All right, let's get started. So we've sort of gathered a basis for understanding probability, and now we're going to just look at probability from that basis. The basis specifically being that of sets. We're going to expand on that, with an idea of counting in the next lecture, which we might start in on today with statistical counting. But what we're going to think about for today as a start is kind of building sample spaces. And we haven't done much of this yet. Usually I'll do quite a bit of this by this point, where we use sort of like a very basic counting system in order to approach an idea of what I'm going to call cardinality. Okay? So there's this term, cardinality. And for cardinality, there are other words that we might throw around. Okay, cardinality is the best word, but there are going to be some other words, and I'll describe that. So the cardinality is simply the number of items, number of elements, members, or whatever word you want to use. I've been using elements. Number of elements in a set. Okay? So this is the number of elements in a set. Other words we might use, might say the word size or magnitude. Magnitude's a good one because it turns out that the way that we represent this, the symbols that we use to represent this, are sort of in line, or the same symbols that we might use for magnitude. So let's just have a simple representation of this. We have some set A, okay? And A contains, let's just say 1, 2, 3, and 4. If we want to represent the cardinality of A, we use these sort of straight bars, and that is going to equal 4, right? There are 4 elements in there that we can discern. So we're going to use this idea of cardinality in relation to probability. Okay, so how does this fit in? Let's say we have a 12-sided die. Okay, and so a single roll of a 12-sided die is going to have the sample space containing elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, it doesn't look amazing, but we know what's in it. All right. So let's say we have a strict subset of S called A. This is a set that is contained by S, and this has the numbers 3, or the this is the subset of rolls of a 12-sided die that are 3, 6, 9, and 12, right? So multiples of 3. If we were to ask, what is the probability that the roll that you get when you roll a 12-sided die, that value will be evenly divisible by 3, we can just represent that as the cardinality of A over the cardinality of S, okay? Which is just 4 out of 12, right? So that's our probability, or, if we reduce this, it's going to be 1/3, or a probability of 0.66. So this is a way to think about probability. This is a way to think about it. And why think about it this way? Because often we're trying to think of all potential outcomes, right? We're trying to think of all potential outcomes, and all potential, there's 100% likelihood or a probability of 1 that we're going to get one of the potential outcomes from a random experiment, right? We're going to get one of those, There's a 100% chance that we're going to do that. But that's not usually the question we're trying to answer. What's the probability of getting one of the potential outcomes? We're usually trying to answer what's the probability of having this one event or this subset of events out of the potential outcomes, right? So often we need to construct a sample space, right? We're going to construct a sample space, and then we want to determine what is the subset. And if we look at the cardinality of the subset divided by the cardinality of the sample space, that is going to be a way that we can define probability, right? That is a definition of probability for us. We're going to find that counting becomes very helpful here. And I'll keep coming back to this. The probability of event A is going to be this cardinality of A over the cardinality of S. And I'll tend to use these same symbols, where S represents our sample space, A represents our subset in which we're interested. So let's think of another die example. Let's use a simpler die. We have a 6-sided die, and so our sample space is just going to be 1, 2, 3, 4, 5, 6. And we're going to define A with a rule. So A is going to represent the set that contains outcomes where there's an even number of pips. And just as a reminder, a pip, if we're drawing a die, a pip is one of these dots. And actually, this shape, this is absolute trivia. I believe this shape is called a quincunx. I might be spelling that wrong, but you never need to know that, so don't worry about that. But this is 5 pips, right? So A here, what we're going to say is A represents all outcomes where there's an even number of pips. An even number of pips. So what is that? Well, it's 2, 4, or 6. And, so this is going to be 2, 4, 6. And we can very easily see that the probability of having a die roll where you have an even number of pips, this probability of A, is going to be the cardinality of A, which is 3, over the cardinality of S, which is 6, or 0.5, right? A probability of 0.5. Note that you can't have a probability greater than 1, at least for our purposes. In the strict sense, probability does not exceed 1. And, there's a model you'll learn about in the DSI, actually, where you get out-of-scale probabilities that are greater than 1, but those aren't actual probabilities. Those are scaled differently. But if we think about what's happening here, we can consider S here, the cardinality of S, to be our scaling factor, right? It's the thing it's the thing that gives the delineation of units, if you want to think about it that way. I think it's easier just to think about it like, well, you have some subset of events, and you have the total of events, and of course, the greatest probability that you can have is going to be this, right? Cardinality of S over cardinality of S, which would be 1. Okay. So let's think about notation. I sort of casually threw some notation in there. Generally, we're going to say probability of some event. This P with parentheses and the event in there. And then we'll say equals something, right? This is just probability of A. That's all. And we can also think about other situations, like the probability of not A, of A not occurring. We can consider things like the probability of A intersected with B, which we might write like that, but I'll be more careful to write this as A intersect B. I think it's nice to use explicit symbols a little more often, even though you don't have to. Of course, if we can intersect, then we have the probability of A unioned with B, right? And here's a new one. We have probability of A given B, okay? So this is new. And we're going to dedicate probably half a lecture just to this when we get to it. There's only one pen and paper day that we take, and really it's a pen and paper half day, where we talk about this type of probability where we have some event given another event. And although that's a very important, let me say it like this. There's a very important way of thinking about probability that leads us to Bayesian thought. And we want to dedicate, a good amount of time. Well, we're going to dedicate half a lecture to that, but it doesn't lend itself very well to coding. So that'll be our one kind of pen and paper lecture when we get there. For the most part, we'll set this aside, though, this dependency. And we'll just look at these first four. But if you see that vertical bar in a probability statement, that just means given, right? That's how we read that. A given B. So A given B. All right. So getting notation out of the way, let's start counting, okay? Probably a lot of you are very familiar with counting. You learned counting very early. And, you probably learned it the right way as far as base 10 goes, right? So what is base 10? We're all very familiar with base 10. We use it all the time. This is just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we roll the 9 over back to 0, and we increment the next place by 1. And, 11, 12, 13, etc., etc. And then when we get this to 9 again, we roll this over to 0. We roll this 1 over to 2, right? And so on. And when we're thinking about this, like if I have the number 973, we have a ones place, we have a tens place, we have a 100s place, right? It's all stuff that, we learned a long, long time ago. Turns out there are other base systems, and this is going to become a handy way to think about probability through the lens of counting. So what happens if instead of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have a different system entirely where our quote-unquote numbers, right, are something totally different, like cat, dog, say ferret, and goldfish. Well, how can these be numbers? They're going to be numbers because we decide they are, just to be very clear. And I'm going to represent cat with a C, dog with a D, ferret with an F, and goldfish with a G. And we're going to imagine that there's some room, right? There's some room where, we've got this door, and we've got these animals back here, right? And what we're going to do is we're going to open the door and pull out an animal, and put it back. We're going to write down what that animal is. We're going to open the door, pull out another animal, put it back. We're going to do that 4 times. And so you can already imagine, well, we could pull the dog out twice, pull the cat out, and then the ferret out, right? We could do that. Or we could pull out the cat 3 times and the goldfish 1 time. But do we have a systematic way that we can figure out all possible ways that we pull out these 4 animals while we pull them out and replace them? What are all the ways that we can do that if we're pulling out 4, right? So each attempt is just 4. Well, we can do that systematically through counting, as it turns out. And this idea of counting, if you study computational sciences, this idea of counting is very prevalent in how we think about things and how we approach things. And I'm just going to give you sort of the basic here. So there are 4 items here, and I'm going to call this a base 4 counting system. Okay, it's base 4, and all that means is that there are going to be 4 places that we can consider. This would be like ones, tens, hundreds, thousands place in base 10. But in this case, we're considering a different place system entirely, and those multiples aren't going to be multiples of 10. They're going to be multiples of 4. But I'm getting a little ahead of myself. Let's think about this systematically. So here's a possibility that we can start at. We draw the cat 4 times. Okay? Here's another possibility. We draw the cat 3 times and then the dog. We can draw the cat 3 times and then the ferret. We can draw the cat 3 times and then the goldfish. Okay, this is not different from the base 10 system. If we're looking at this, if we're really thinking about it, what's going to happen here is, we counted cat, 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 dog, cat, 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 ferret, cat, 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 goldfish, and now that we've exhausted the 4 possibilities in this furthest right column, we're going to we're going to roll goldfish back over to cat, and we're going to roll this next cat over to dog. Okay, so now we've got cat, cat, dog, cat, 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 dog, dog, cat, cat, dog, ferret, and then cat, cat, dog, goldfish. And we can continue doing this. At this point, we would roll goldfish back over to cat, we would roll dog over to ferret, and do this again. So if we follow this process to its the furthest that we can follow it, we are going to eventually end up with the last thing we're going to get is the last 2 are going to be goldfish, 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 ferret, and goldfish, 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 goldfish. That's how we could build a sample space of possible orderings of these animals that we're pulling out of this room. Okay? So how do we do that with code? Turns out it's strikingly easy. Programming really lends itself to this. So we've got these pets, and I'm just going to do cat, dog, ferret, and goldfish. And I'm going to have our outcomes. I'm going to collect all the different ways that we might draw these 4 animals out of this room. This is what we call with replacement, by the way. We'll use that term sometimes. This is sampling with replacement. With replacement. Replacement. The reason we call it with replacement is we're pulling a cat out, and we pull the cat out and we put it back. So we can pull it again, actually. You can also think about this as we have, some infinite number of cats, dogs, goldfish, and ferrets in this room. That's another way to think about it. Some sort of different dimensional space that we can pull from. Okay, so how do we do this systematically? In code, we can do this. We can do it with loops. So I can say for pet1 in pets, and I can just do this 4 times. And pet2, pet3, and pet4. And I'm just going to do this. I'm going to say outcomes.append, and I'm going to append a list that is pet1, and then pet2, pet3, pet4. So pet2, pet3, pet4. Copy paste is your friend. And at this point, I am counting in this number system. All right. So I'm going to say for pet outcome in outcomes, let's just print that pet outcome. Okay. All right. So let's look at this. We start off with all cats, then all 3 cats and a dog, 3 cats and a ferret, 3 cats and a goldfish, cat, cat, dog, cat, 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 dog, dog, cat, and so on and so on. We end up down here with all goldfish as the last value. Any guess how many different outcomes there are? Does anybody have a sense of how many different outcomes there are? Of course, we can simply do this. We can print the length of the outcomes to see this. But yeah, anybody want to put a guess out there? Yeah, exactly. So there are 4 to the 4 different outcomes, or 4 to the 4 outcomes that are unique. So 4 to the 4th power. Now, how do we want to think about this? Let's think about this in terms of place value. Okay, I'm just going to erase a little bit of this. Actually, I'm going to just erase the whole thing. If we have, let's say, cat, 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 cat. So here are 4 places. This is just the first example. This is the 1's place. This is the 4's place. Okay. So let me do it like this, actually. This is the 4 to the 0's place. This is 4 to the 1's place, 4 squared's place, and 4 to the 4th place. Oh, sorry, 4 to the 3rd place. And so this is our 1's place, this is our 4's place, our 16's place, and what is that, 64's place. Okay. And we could translate this to a numeric value, but the reason why we have, one way to think about how many different possibilities we have is if we maximize all of these places, right, 64 plus 16 plus 4 plus 1, that is just going to be 4 to the 4th power. So we can see that. All right, so let's just verify that. So I'll just print 4 to the 4th power. And indeed, there's 256. Okay, so what we've done here is we've built a sample space. This outcomes is a sample space that we can consider as our S. Okay, so what we can do from there is we can define a subset of S, right? And I'm going to leave this to you. I'm going to give you a prompt, and this is just going to simply be, what is the probability that a person will select 2 or more cats? You're going to have to use the code that I dropped in the Slack and you're going to answer what is the probability that a person will select 2 or more cats when randomly choosing 4 pets. And that's 4 pets with replacement, as I said. So let me set a timer for 4 minutes and see if you can answer that. If you use code to answer it, and that's what I'm going to encourage you to do, if you use code, also paste in your code prior to answering this probability. Okay, so let me give you 2 more minutes. Oh, let me see. I see a couple answers coming in. That looks good. Let me give you 2 more minutes on this to try to figure it out. And then I'll go through an answer. We're going to be doing this type of thing a lot. Okay. okay? And we're gonna, this is sort of like the soft intro to it. So let me just give you 2 more minutes. Okay, so I'm going to go through a solution for this. What is the probability that a person will select 2 or more cats when randomly choosing 4 pets with replacement? So I could make a collector here called 2 or more cats. All right, 2 or more cats. I'll make that an empty list, and I'm just going to traverse the outcomes and collect all the outcomes where we have 2 or more cats. So I'm going to say for outcome in outcomes, if let's say if outcome dot count of, I think I just used capital C, if that count is greater than or equal to 2, then I'm going to say 2 or more cats dot append the outcome, and we can just print the length of the outcome over, the length of 2 or more cats over the length of outcomes, right? This is our cardinality of A, which is the subset that we're considering, over the cardinality of S. So if I run this, looks like it's 0.261 or 0.262 roughly. So that's a way that we can do this. You could do a counter instead of a collector. Either way should be fine. But what you're essentially doing here is you're establishing the cardinality of a subset and dividing it by the cardinality of the sample space. Okay, so I'm going to have you, let's see, let me look at these next 2. Yeah, I think this is good. Okay, so this one I'm going to give you some starter code, and let me just throw that in the Slack. And you are going to write a function called series of flips. And I have this set for 4 minutes, but let's do 6 minutes on this. So you're going to write a function called series of flips. It is going to depend on this coin flip. You're going to define a parameter n that represents the number of coin flips, and you're going to return a list of length n containing n random coin flips. Okay? So there's a new thing I'm introducing here. This is the random function, all right? Sorry, the random choice function. And if you look at what's happening in this code, choice is going to pull a random value out of flip, okay? So you're either going to get a heads randomly or a tails randomly. This series of flips function needs to populate a list, all right? So if you really hit a wall on this, don't worry, that's fine. We're going to be doing a lot of this. But this is sort of like a challenge to see where you're at right now. So I'm just going to set a timer. I'll set a timer for 6 minutes. Go ahead and code that function. Okay, so this is a bit of a little bit of a curveball, but we're going to tie this in. This is sort of a random thing happening here, right? There's sampling that's happening, is how we'll start talking about this soon. And this is a little bit of a deviation from counting, but we're going to think about this in kind of a similar way, sampling and counting. So here we've got this coin flip, and we need to write a function called series of flips, okay? Series of flips, and we want to flip n times. So I'm just going to collect the flips, and return those. And I'm going to say, the way I'm going to do this is I'm going to say for whatever, this little underscore, I read that as whatever. For whatever in range, and I'm going to do this n times, I'm going to call out to coin flip, right? I'm going to call out to that coin flip n times. The result of that coin flip, I'm going to append to flips, right? So flips.append coin flip. Oops. And we can return flips. So let's run this. Let's see. Let's just print a series of flips, and we'll flip the coin 10 times. So here's one outcome: heads, tails, 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 heads, tails, tails, heads, heads, tails. Right, and of course, if I do this again, we're going to sort of continue to see different outcomes. So we can expand on this idea a little bit, and take a slightly different view of probability. All right. Instead of explicitly counting, we can and determining an exact probability, we can estimate a probability from this. So let me give you this code first, and then we'll kind of go from there. I just want to show you a way we might estimate this. So let's talk about the probability. Let's say I don't know, the probability of getting 8 heads in 10 flips. Now, we don't have an explicit way to do this yet without using that nested for loop structure, right? But what we can do is we can let's say, sample 1,000 times. All right, we can perform 1,000 10 flip samples. We can do that, and we can count how many, not namey, but count how many have 8 heads. We can do that. That's something we know how to do. And so let me just go ahead and code that really quick. So let's say 1,000 flips. So how many flips are we gonna? So the number of flips, or sorry, number of trials of 10 flips is going to be 1,000. And I'm gonna say for whatever in that number of trials, and range that number of trials. And we're going to call out to series of flips. So we're going to get a result, an outcome from series of flips with 10 flips, right? We're going to say res.count of h for heads. If that is equal to 8, then we're going to increment a counter, right? So if that is equal to 8, we're going to say 8 heads plus gets 1. Of course, we need to establish this counter up here. And we'll start it off at 0, simple accumulator. And what you can see here is that even though we're not going to get an exact answer, and I'll run this more than once, and we'll see that that answer will vary. We're not going to get an exact answer, but what we're going to utilize here is still, we've got a number of trials, a number of experiments that ends up giving us something like S, but it's not exactly the sample space. We're estimating the cardinality of A over the cardinality of S here, instead of getting it explicitly, because of course we can have multiple outcomes that are the same. But this is going to give us a different lens on probability. So if I run this, I can simply say this is going to be 8 heads, how many times that occurs, over the number of trials. Okay? So this is another view of probability. So looks like probability of 8 heads could be around 4.3. Let's run that again. 0.043, or 4.3%, 4.7%, 3.9%, 5%, right? So we're seeing a lot of variation here. A lot of, there's a fair amount of variance here. And, one thing we could do is we could run this over and over again and take the mean. And what we're likely going to see is something that gets really close to the actual probability of 8 heads and 10 flips. I'm going to be a little hand-wavy about that because we'll drill into that quite a bit in a couple days when we start getting into distributions. So we're going to, let me give you this code so you can play around with it. Feel free to extend it to verify what I'm saying. That if you take if you run this over and over again and collect this result, you know what? Got a couple minutes. I think we're a little bit ahead, so let me just do that, okay? Instead of doing this, why don't we do this? Let's do this whole thing another 1,000 times, okay? So whatever in range, we'll do this 1,000 times. And we're going to also collect the probability estimations, okay? And down here, I'm going to say probability estimations dot append. We're going to append that result. Unless I misspelled something. Oh, just missing a colon. Okay. So now, what we could do, why don't I just print, I'll do two things. I'll print the probability estimation so we can take a look at it. And I will also print the mean of the probability estimations. Okay, so that's just going to be probability estimations divided by 1,000, because that's how many times we are doing that. Okay. So it's going to take a little bit to run. Notice we have a nested loop here. So this is 1,000 of 1,000. Oh, right. That makes sense. I actually need to sum the probability estimations. That's my bad. And we should get, kind of a big wall of numbers as we see above. So, if we just scan through this, I know this is sort of like hard to see in this form. Let me take a look at this a little bit closer. Not sure why we're getting numbers greater than 1. Eight heads divided by... Oh. Sorry, there is an error in my code in here, I believe. So, count of H, 8 heads, number of trials. Why am I getting numbers greater than 1? Does anybody see where my error might be in here? Need to put 8 heads in the for loop. Oh, wow. Yeah. Thank you so much. That absolutely makes sense. So I need to reset 8 heads every time, otherwise, because this number is just going to keep growing, right? As we can see, it is definitely growing. Okay, perfect. Okay, let's try that again. All right, so what we should see here is if you're familiar with a normal distribution, our assumption is actually that values are going to be normally distributed likely around this estimation, this point 0.0435. So we should have some kind of bell curve around that, greater than and less than to some. So what we could also look at is the minimum here, right? I think that is interesting. So let's look at the minimum value for the probability estimations. And let's also look at the max value. Just to gain a little more insight into this kind of estimation process through sampling. And let that run. Oh, did I just do min twice? I did. There we go. All right, one last time. And what you're also going to notice here is that this 0.0439, we're not going to have, like, how do I say this? The more samples we take, the more trials we do, the more that this value is going to settle, okay? This is different from the last time. It was 0.0439. This time it's 0.0435. And these are going to change a little bit too. Keep that in mind. We're going to look at that with a little bit more depth, but not today, but we'll look at that very soon. All right. So I'm going to have you code up something really quick. We're going to kind of leave this aside for a little bit. And we're going to come back to sampling quite a bit before very long. But what I'm going to have you write instead is going to refer back to what we've already done in terms of counting. You're going to write a function called forFlip sample space. It's not going to take any arguments, and it should return a list of all possible outcomes for 4 coin flips. So with that, I'm going to set a timer for 4 minutes. Yeah, and go ahead and code that up. Okay, let's build this sample space, and then we'll take a break. So this kind of goes back to that first pets, the pets function, or not function, but the pets example that we started off with. I can say for, get a little more space here, for flip sample space, doesn't take any arguments, it's just going to return a list. So I'll just say, I'll just call this for flips, and we'll say we can do, call this outcomes. No, I won't call it that. I'll just do it like this. So for flip 1 in heads, tails, I actually like doing this the other way, tails, heads. And we're just going to do this 4 times. 2, 3, 4. 2, 3, 4. We can say for flips dot append, and we're going to append a list that is flip 1, flip 2, flip 3, flip 4. 1, 2, 3, 4. And we can take a look at this. If we say for outcome in, and in this case I'm just going to grab the function name, because that will return a list that we can traverse. I'll just print the outcome. Oh, something else is running, of course. Let me just comment this out. Try that again. None type object is not iterable. I am not returning for flips. Right? Since I'm returning none, I can't iterate over anything. So let's try that again. Okay. So here's our sample space of 4 coin flips. We're going to think about this a little bit more, okay? After the break. So let's take a 6-minute break, and I'll see y'all back here in just a little bit. All right, let's jump back into this. So let's see. Make sure I pasted that in. All right, I still need to paste this in. So here's our 4-flip sample space with a fair coin. Oh, sorry, let me fix that. Okay. So using that code, we're going to answer a simple probability question, okay? And I'll give you 4 minutes to answer this. So reference that previous breakout solution. What is the probability that in 4 coin flips you get exactly 3 heads? Doesn't matter where those 3 heads occur, right? It could be the first, third, and fourth. And you're going to consider the sample space of A, the cardinality of A over the cardinality of S. So let's just answer that really quick. Include your code that you use to solve this. I know you can solve this without code, but I want you to write code to solve it. Demonstrate it. The length of something over the length of something else. So go ahead and do that. Okay, let's solve this. This looks a lot like things that we've already done. And, you know, just trying to sort of hammer this in. So let's call this outcomes. And we've got the outcomes from the 4-flip sample space. I can just say, I can just collect these. So 3 heads. You can say for outcome and outcomes, if that outcome dot count of heads is 3, then we can say 3 heads dot append. We can append the outcome, and we can just print the length of the 3 heads divided by the length of our outcomes. And that's going to be cardinality of A over cardinality of S, right? So let's see what that gets. Looks like that is 0.25. So if we wanted to, you know, really look into why that is, we can traverse our outcomes, we can traverse the ways that 3 heads occur. Okay. So here's a caveat that I want to introduce. So let's say we call that series of flip function. Remember the one with the random selection of flips, right? So we call series of flips. And we put a number of flips at 14. Okay. What is the probability that we get all H's? So what is the probability of all heads in 14 flips? And how do we start thinking about that? How do we approach solving that? Are we going to do 14 nested for loops? We could, right? That's something we could do. But it turns out that if we're thinking about this in terms of counting, right? And we have a base 2 system, right? This is base 2 that we're considering, where the 2 values are either tails or heads. Then we can kind of break this down very simply. We can say, well, all heads. So what does that look like? That's heads 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. How many ways can this occur? It turns out there's only one way that this can occur, right? Because we only have heads or tails. There is no other way to get all heads. This is the only way. However, there are a lot of different ways that, you know, like we could have all heads and then a tails, and that would be 13 heads, right? We could have, you know, heads, then a tails, then a heads, and that would be 13 heads. So there may only be one way to get 14 heads in 14 coin flips, but there are obviously a number of different ways to get 13 heads in 14 coin flips, okay? But this problem itself, this problem that we're thinking about here, the probability of all heads, happens to be just easier to solve. And there's a couple different ways we can solve this that are, when you see it, they're actually equivalent. So we can look at the probability. Well, let's start small, actually. Let's start with the probability of getting heads on a single coin flip. Let's think about that first. So the probability of heads in one flip. Well, sorry, let me use color here. Use dark blue. So what are the possibilities? We can get heads or tails, right? And that is the winner right there. There's a probability of heads, getting heads in one coin flip. Sorry, that's all heads in one. It's just 0.5, right? There's two possibilities. And we can see here that that is just 0.5. So what about the probability of heads in two coin flips? So let's think about that. Two coin flips, well, what are the different ways we can do that? We can get heads, 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 tails. Well, why don't I do it like this, since I started that? Tails, 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 heads, heads, tails, heads, heads. How many different ways can we get all heads? Just one out of 4, right? And so the probability of all heads, all heads in 2 is going to be 1 out of 4. Equals 1 out of 4. You might be already thinking about the pattern here. So let's think about this in 3 flips. All heads in 3 flips. What does that look like? So I'll start there. So let's write down all of our possible ways of getting this. Tails, tails, tails. Tails, tails, heads. Tails, heads, tails. Tails, heads, heads. I'm just counting, if you notice. And then we can go heads, tails, tails. Heads, tails, heads. Heads, heads, tails. Heads, heads, heads. So how many different ways can we get all heads here? Well, there's just this one. Again, still just one. So the probability of all heads in 3 is just going to be 1 out of, well, 1, 2, 3, 4, 5, 6, 7, 8. So let's think about this denominator and how it's growing. So it was 1 out of 2, then it was 1 out of 4, then now it's 1 out of 8. What's the next one going to be? For all heads in 4 flips, I think we can see a pattern here. 2 to 4, 4 to 8. Let's assume 8 to 16. Okay. So 1 out of 16 different ways. So this is, if we're thinking about this, this is just 2 to the first power. This is 2 squared, 2 to the third power, 2 to the fourth power. Another way that we can think about this, and I think this is a very convenient way, and is a basis for understanding probability in general, this sort of basic probability. The probability of getting heads on the first run of this is 0.5, right? And the probability of getting heads on the second flip is 0.5. The third is 0.5. The fourth is 0.5. And it turns out we can just multiply these together. And we could do that for all 14, and we could say the probability is going to be 0.5 to the 14th power, which we could also represent as one instance of success, one possibility, all heads, out of 2 to the 14th. Possible ways of doing that. So this is a helpful construct, all right? This is a helpful construct. And this extrapolates to some other things. And I'm just gonna, mention this. These coin flips do not affect each other, right? Getting heads on the first flip does not affect getting heads on the second flip. Getting heads on the second flip does not affect getting heads on the first flip. Okay? There's no effect there. So let's make a different problem. let's think about a different problem. Let's say on your first, the first thing you're going to do is you're going to flip a fair coin. The second thing you're going to do is you are going to roll a 6-sided die. The third thing you're going to do is you're going to select a card from a standard deck, so from 52 cards. What is the probability of getting heads, 2, and then let's say a queen? What is that probability? Given what we understand of these being unrelated things that we're doing, right? Whether or not we get heads or tails does not affect the roll of the die. Whether or not we get a 3 doesn't affect whether or not we get a queen or not. So how would we multiply this? Very much the same way as if we were to just use subsequent coin flips and multiply the probability of getting heads every time, okay? And, you know, we can just fill this in, like 0.5. And then this is just 1 out of 6. And this is just 4 out of 52. And, you know, I don't know this offhand, but we could throw that into a calculator and see the answer. But the point being, we can do this. We can ask these sorts of we can answer these sorts of probabilities. There's only one way for this to happen, and we know the probability of each event. And so, actually, there's more than one way we could get different queens, but that's not so relevant. There's still only 4 out of 52 here. We can just multiply these together. And, you know, I'm just going to bring this back to the coin flips. You know, all heads in 14 flips, the probability of that, of all heads in 14 flips, is going to be the same as the probability of any specific sequence of heads and tails in 14 flips, okay? These are going to be the same, all right? And I mean a specific sequence. I don't mean the count of heads. I mean the probability of, you know, heads 14 times, right? Versus the probability of, you know, heads, tails of this specific sequence. 1, 2, 3, 4, 5, sorry. And, you know, out 14 times. These are going to be the same probability because there's only one instance that looks like that we, you know, out of all the instances. Notice that there is a specific sequence here that we are maintaining. There's only one instance of each. What we are not doing is we are not saying what is the probability of getting 4 heads in 14 flips. That's a different question. And that brings us into the next topic. So we're going to get a start on statistical counting. And you're probably thinking, well, haven't we been counting this whole time? Yeah, we have been. And, you know, we're taking this idea of a subset and the containing set and thinking about that, and we're going to evolve that, and we're evolving that with counting. And we started with this very basic counting, right, where we've got symbols that we're using as quote-unquote numbers, and we're able to increment them for any number of places and any number of symbols, right? We used cat, dog, ferret, goldfish, and we could make it a 20. We could put 27 symbols in there, and it's going to be the same counting process. We'll have a base 27 system. We're going to have a ones place, a 27s place, you know, and so on. It's going to expand very fast if it's 27, but it's going to be the same fundamental process. So we can evolve from there, okay? We've been talking about counting in its sort of raw form, okay? And this is counting where we have an idea of replacement, right? We pull the animal out of the room, we put it back in the room so we can select it again. What happens, though, when we don't deal with replacement? What's that? What if we say without replacement? What happens if we start talking about without replacement? How many different ways can you select 4 animals from a room without replacement? Those 4 animals. And this is going to evolve our idea of counting. All right. So without replacement. First thing I'm going to think of, well, the first thing that we're going to talk about, we're going to be a little bit roundabout with this. We're going to talk about factorial, okay? And this is just represented as some number factorial. Let's say we have 9 factorial. This is just 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. It turns out that this is the number of different ways, this calculation is the number of ways that we can arrange 9 objects, okay? This represents, for us, represents the number of ways to arrange 9 objects. Okay? So let's think about this with a simpler number that we don't have to calculate so much. Let's think about this just with 3 factorial. And let's think about cat, dog, and hamster. So we've got these 3 animals, which I'll just represent with C, D, and H. So let's count in this system. We'll start with counting, all right? We'll start by saying, let's start with replacement. And I'm going to say, let's change color here, and we'll just say cat, cat, cat. This is, take the cat out of the room, put it back. Here's a possibility. Cat, cat, cat. Cat, cat, dog. Cat, cat, hamster. Cat, dog. Cat, cat, dog, dog. Cat, dog, hamster, right? And then we've got, oh gosh, cat, hamster, cat, cat, hamster, dog, cat, hamster, hamster. And then we increment this to dog. So we have dog, cat, cat, dog, cat, dog, dog, cat, hamster, right? And we're filling this in. So then we get dog, dog, cat, dog, 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 hamster, dog, hamster, right? Yeah, dog, hamster, cat, dog. I could have used maybe less items than 3 to be a little more timely, but so dog, hamster, dog, dog, hamster, hamster. We're sort of in the final stretch here. Not really. I'm realizing hamster, cat, cat, hamster, cat, dog. And I'll probably just leave off in just a second with this so that we don't go too down the rabbit hole, but or the hamster hole. So hamster, cat, hamster, hamster, dog, cat, hamster, dog, dog, hamster, dog, hamster. Oh, we're almost there. Okay. Hamster, hamster, cat, hamster, hamster, dog, hamster, hamster, hamster. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oh, good. we do have the right amount here. Okay. So this is obviously without replacement, right? This is if we can pull them out of the room and put them back. But we can reduce this space to represent the different orders that we can pull them out of the room without putting them back. So how do we do that? Well, we just remove anything that has duplicates, and we'll be able to see the different arrangements of these items. Okay. And point out any that I get wrong here. Okay. So if I just rewrite these, this is CDH, cat, dog, hamster, cat, hamster, dog, dog, hamster, dog, cat, hamster, dog, hamster, cat, hamster, cat, dog, and hamster, dog, cat. 1, 2, 3, 4, 5, 6. 3 factorial is indeed 3 times 2 times 1, which is 6. So that's taking a sort of reductive approach, which we're going to do a lot in statistical counting. We're going to take reductive approaches, and then we're going to take approaches that reorder things. So this gives us a sense of all the different ways that we can order 3 items. All right. I'm going to point out something to you. How many different ways can we reorder 0 items? Or how many different orders can there be for 0 items? This is sort of philosophical, but there can only be one. Okay, so if you ever see 0 factorial, if you have 0 items, how many ways can you arrange them? Well, 1. So it's a little bit weird to think about it that way because you don't have any actual items to arrange. But there's 1 arrangement of 0 items. I just want to point that out because it does come up from time to time. Okay, so let's rewrite this idea. So we have selection 1, selection 2, and selection 3. And this is still working with those same items from before. So cat, dog, and hamster. So these are the different ways that we might do this. This is an easier way in some ways to represent this. It's not reductive. So if we select a cat, then there are 2 different things we could select in selection 2. We either select the dog or the hamster. We select the dog, we select the cat or the hamster. We select the hamster, we select the dog or the cat. And this necessitates the final selection. So cat, dog, hamster, cat, hamster, dog, dog, cat, hamster, dog, hamster, cat, hamster, dog, cat, and hamster, cat, dog. There are 6 ways to do that, and we can see it. And we can also answer a probability, what is the probability of selecting a cat on the first draw? Well, that's just these 2 paths over 6 paths, so 2 out of 6, right? So probability 0.33. So this is another way of thinking about this. And this is going to lead us into something. But the first thing I'm going to have you do before we get there is code factorial. Okay? So recall the factorial of a number, like let's say 3 factorial, or 6 factorial, is just 6 times 5 times 4 times 3 times 2 times 1. You're going to write a function called factorial that is going to take a value n and return the factorial of that. So I'm going to give you 3 minutes to code that. And go for it. All right, so let's code this up. Factorial is one of those functions that should, we'd expect you to just be able to code up on the fly. Once you have a fair level of proficiency, it's one of those things. It's simple accumulator pattern. Has a multiplicative accumulator, not a summation, but we would expect you to just be able to code this up pretty quickly, pretty soon. So we're going to pass in some number, right? Could be 6, could be 5, I'm going to start a product at 1, and I'm going to say for each number in the range, and we'll start at 2. I could start at 1. Doesn't really matter because anything multiplied by 1 is just itself. So might as well start at 2. And I'm going to go up to the number including it, and I'm going to just say product times gets n, and we can return that product. So to test this, factorial 5 should be 120. So factorial of 5 should be 120, and it is. Okay. So if you have 5 objects, you can arrange those 5 objects in 120 ways. So I'm going to answer this next question, this next breakout, just to give you an example of this. of how we might apply this. Okay. So there are 10 people standing in the line for beignets at Café du Monde in New Orleans. How many different ways could the 10 people be arranged in the queue? So let's think about that first. You've got 10 people. How many different ways could 10 people be arranged? Turns out that's just 10 factorial. Right? Just 10 factorial. All right, given that the line was formed organically, people got in line. However, what is the probability that they are standing in the queue in alphabetical order? And let's assume everyone has different last names, so there's only one way that that could occur, right? So what is the probability of that? The probability of this alphabetical ordering. This is just going to be 1 over 10 factorial, right? Which is a pretty small number, just thinking about it. So 1 over, actually, let's see what that is. 1 divided by factorial of 10. That is a, like I said, very small number. 0.000000275. Okay. So the reason I wanted to just sort of do that one is I want to get us into permutations. And we're going to, I want to introduce permutations. We're going to build some underpinning of permutations tomorrow. Some more intuition around it. So there's this idea of a permutation. And let's associate this word with arrangement. Okay? A permutation is an arrangement of items. It has an order, right? And the thing we say here is order matters for permutations. It matters in what order those 10 people are in line. Okay? The thing about a permutation is it doesn't have to be all 10 people. Okay? So we might take this idea of 10 people and ask, how many different ways can we arrange 4 of them? 10 people, arrange 4 of them. And the way we might state that is 10 permute 4 of them, right? But we can write this much more simply in this form. We can just say 10 capital P 4. 10 permute 4. Okay. So that's how we might do that. The thing to think about first is that if you have 10 people and you're arranging all 10 of them, there are going to be more ways to do that than if you have 10 people and you're going to arrange 4 of them, right? That just stands to reason. We're only going to have like these 4 things left that we're counting. And because of that, we are going to reduce the space. Okay? So just like we went from raw counting, counting with replacement, we reduced that to factorial. Factorial is actually just a special case of permutations where we say, okay, we're going to permute everything. We're going to say 10 permute 10, for instance. Okay? So let's take that idea. We have factorial, which is n factorial. Now, let's say, and I'm going to just draw this out with, just some sort of equivalent to 10 factorial. How else can we think of 10 factorial? Well, we can think about it as 10 factorial over 1, right? Well, if we really want to think about it, we know another way to get 1 is 0 factorial, right? So we've got 0 factorial. 0 factorial equals 1. We could replace this 1, right? We could say this is actually 10 factorial over 10 minus 10 factorial, right? This is going to be the same thing. Or here we're going to say this is n factorial over n minus n factorial. Turns out this gives us insight into how to reduce the space for permutations smaller than n. All right? So if we want to take this a step further, we can decide that instead of permuting everything, we're going to permute k. We're going to permute k of these things. And as a result, we're going to reduce the space. So it's going to be n factorial over n minus k factorial. Okay. So how does this play out in practice? It turns out that this is n permute k. When we get down to it, that's n permute k. N factorial over n minus k factorial. How does this play out in practice? So say we just care about 4, arrangements of 4 out of these 10 people. So maybe only 4 of them can be served, before we close or something like that. How many different ways can that happen, given that there are 10 people and we can only serve 4 of them? So let's break this out. We've got 10 factorial over 10 minus 4, the result of that factorial. So we can say this is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 10 minus 4 is 6. It's going to be 6 times 5 times 4 times 3 times 2 times 1. And we can, eliminate these, the 6, 5, 4, 3, 2, obviously the 1. And the result of this is going to be, 90, 720, I should just be able to do that in my head, but the result of that is going to be simply 10 times 9 times 8 times 7. So 5,040 different ways that we can permute 4 out of the 10. So again, just to reiterate that's if you have, this is our base system, you could say, right? N is our base system, or the number of objects that we're trying to arrange, and we're going to permute k of them. This is going to be the number of the arrangements of all of them reduced by the number of arrangements of sort of like something like the complement. It's not exactly the complement, but we're eliminating out the rest of them. So if we're permuting 4 of them, we're not permuting the other 6 at any given moment, right? So we are going to eliminate out 6 factorial in this case. So that's just some underpinning of what's happening here. It turns out that we can, just like we discovered all the permutations through factorial, we can do the same thing. Just how we discovered the different arrangements through a reductive approach by raw counting with replacement, reducing out the space, we can do the same thing with permutations, and we will. I think at this point, I already kind of demonstrated this with 3 items, so I'm not going to demonstrate that again. But you know what? I think we do have enough time to just do this last breakout. I'm going to have you code permutations in the next 3 minutes. We only have about that much time. So here's the permutations formula. Go ahead and write the permutations function. All right, so I have very little time to write this, so I'll write it very quick. So permutations, n permute k. This is just going to be the return of that mathematical function. So that's going to be the factorial of n divided by the factorial of n minus k. I personally believe that you should cast this to an integer, given that it is a count. We're not going to have partial values. Let's see if I can code a different form of this that I think is a little more optimal, where we start our permutations at 1 and we treat this a little bit like factorial. So I'm going to say for I in range, I'm going to go from n, so the actual value of n, down to n minus k. So I'm implicitly performing that reduction, that fractional reduction, and for each of those, I'm going to multiplicatively increment the number of permutations, and we can return permutations like that. So let's test that out with 10 permute 5, just to make sure I don't have an error in there. And then we will call it an evening. Oh. 10 permute 4, which should be 5040, right? And let me just make sure that I don't have an error in the other one. Okay, great. And we can go back over this slightly more optimal version next time. Yeah, that is in the Slack. And let me just